Hi everyone, this is the video for tutorial 4 of Econo 4. We're going to be covering both questions in this video, and hopefully it'll be helpful. Again, disclaimer, this may not be right, don't take whatever I say as gospel, this is just advice. Anyway, let's get started. So, let's look at the first question. Suppose that Wales passed a law requiring employers to provide 6 months of paid maternity leave in 2006. You are concerned that women's wages will drop in order to pay for this new benefit. You find the dataset that samples men and women in Wales and Britain has information on wages. You pull two cross-sections, one from the year before the law took effect, and one from the year after, and you find the mean wage in pounds per hour for various groups is as follows. So you can see here the relationship. Wales goes from 8.6 to 10.2. England goes from 9.1 to 11.7. Okay? So a 1.6 difference in Wales compared to a 2.6 difference in England. So, it says here, suppose you use England as your control group, where this law was not passed. Illustrate the difference in difference estimator of the effect of this policy graphically. Now, to illustrate what a difference in difference estimator is, let's look at our diagram over here. So as you can see here, we have three lines. We have the control group, as you can see on top. We notice that England has a higher value than Wales, so it is going to be above. Remember, we're also plotting the characteristics of our data on the axes. So we've got wages here on the y-axis, and time, or years, on the x-axis. We set up our two periods, before 2006 and after 2006, and we can see here England as the control group is 9.1 to 11.7. Now, if we gained the same expectation from that control group for Wales, we'd expect the gradient to be the same. So we copy the line and then we put it back there. Okay, this is our expectation. But the Wales actually has a much lower rate of growth, 1.6 instead of 2.6. So in fact the line is actually much shallower. Now you cannot, I know other diagrams look a bit more like the treatment group line is in between two lines, but in this case, because we're essentially decreasing, it's going to have to be a negative effect. Okay, so we've got here the effect of the policy. Great, so we've got that summarized. Now, to calculate the difference in difference estimator, as it asks for here, we need to, first of all, if you guys can sort of see this, hold on, can I? Yeah, hold on. Can I show this? No. Okay, well, hopefully it'll do it. There we go. We've got this big table here. Okay, now what we want to do is we want to calculate the differences in our groups, first of all. So we've got a difference between 8.6 and 9.1. What we're going to do is we're going to subtract the second. We're going to subtract the first from the second. No, the second from the first. Yeah. So, yeah. So first minus second, essentially. So for the first one, we get negative 0.5, and for the second one, we get negative 1.5. The difference between both of these is actually going to just be negative 1. Okay, so our DID estimator here is negative 1. I think that's fairly clear. What assumptions is your estimate of the impact of the policy on female wages unbiased? Do you think this is a reasonable assumption? So we assume that, from our diagram above, as you can sort of see here, we're assuming that in the absence of treatment, both the control and the treatment group would have this constant gap. As you can see with these two orange lines, we're basically saying in the absence of treatment, they're going to be essentially parallel to each other. I think there's a word for this, but I think it's like the parallel relationship, essentially. So obviously this is unrealistic because different countries will have different qualities and omitted variables that we may not be considering. So this is not necessarily a good assumption to make, although it does help us to formulate our model. Okay. So for example, you can have different socioeconomic factors that could affect different parts of the labour market in each country. So it may not necessarily be the same gradient here. What's number 4? You run the following regression on your sample. So we have wage is equal to alpha plus beta 1 after plus beta 2 Wales plus beta 3 Wales times after plus mu. And we've got dummy variables here. So after is a dummy variable. After is the value of 1 if we're after 2006 and 0 if before. And Wales is a dummy variable that signifies if we're actually from Wales. Now, it wants us to figure out which regression coefficient measures the difference in difference estimate of the policy. Well, it's actually beta 3, but I think it's a bit hard to see how we do that. So let's think about the conditional aspect of this. Say we have someone from Wales before 2006, okay? So for that, we'd have Wales equals 1 and after equals 0, right? This would also correspond, if you can think about that here, to this section up here, the top left corner in the table. So it corresponds to 8.6. It also corresponds to essentially setting the dummy variables to 1 and 0 respectively. Okay? 1 for Wales and 0 for after. So we know that alpha is going to be included, but beta 1 isn't because after has a value of 0. Beta 2 is going to be included because Wales has a value of 1, but beta 3 won't be because remember after has a value of 0. So we can see that if Wales is equal to 1 and after is equal to 0, we can see that the coefficients we're essentially getting are going to be alpha plus beta 2. And because we know that that is equal to 8.6, okay, we can sort of, well, that's actually for later, but essentially we're categorizing things conditionally, okay? So, for example, if the person was not from Wales and it was before 2006, we would categorize after and Wales as 0, and we'd just be left with alpha, as you can sort of see here in my notes. Okay? Of course, as usual, I'll post my notes to the description in case you guys want to check them out. Anyways, to calculate the difference in difference estimator, we've got to do it for different time periods. So you can see here that we've got both times before 2006. We already established that this one is going to be alpha plus beta 2. What about England, so not Wales, before? That's going to be 0 all around, right? So that's going to be alpha. So we need to calculate the difference between alpha plus beta 2 and alpha, which surprisingly enough is beta 2. So then doing the remaining ones, if both equal 1 here, Wales after 2006, all the coefficients are going to be included, alpha plus beta 1 plus beta 2 plus beta 3. And if we just take away Wales, we're going to include all the after ones. So it's going to be alpha plus beta 1, just that. So what's the difference between these? Well, it's actually going to be beta 2 and beta 3. So our first difference was beta 2, and our second difference was beta 2 and beta 3. So what's the difference in the differences? Well, it's beta 3. So that's how we get it. Also, there's a bit more of an intuitive way of looking at it. Given that both this variable over here is Wales times after, we would expect that it would be satisfied essentially in the case where we're looking at both of the aspects, really. But that's not this very rigorous, so we essentially use this method to tell us that the coefficient that measures the DID estimator is beta 3. Now to calculate what we've got here, we're going to relate these values to what we got earlier. So we said, for example, let's say we had Wales before 2006. Wales would be equal to 1 and after would be equal to 0. Okay, so let's look at that here. We would have alpha plus beta 2. Okay, so alpha plus beta 2 equals 8.6. What's more, if we do England before 2006, that's just equal to alpha because it's 0 for Wales and 0 for after. So 9.1 equals alpha straight out the gate. Okay? If you do this for all of these, you should get a sequence of equations that looks like this on the right side, if you can see that here. And this is fairly easy to solve. Once you've got alpha, you can pretty much get the rest. It's very easy. But yeah, that's pretty much it. I don't think that one's too difficult. There is a bit of intuition there that's a bit non-obvious, so to say. But this is pretty much how you would do it. There's also different ways of notating this. You could put this in expected value terms, conditional probability terms, whatever you guys prefer. Right, we've got question 2 here. You're given data on food expenditure, income and demographic characteristics of 150 married couples, where the husband is a manual worker and is aged 30 to 50. All survey interviews take place in the same month. You decide to estimate an angle curve and regress the ratio of food expenditure to income, WFOY, on the logarithm of net current income, NCY. The number of children aged 6 to 10, kids 2, the number of children aged 11 to 17, kids 3, and an indicator for London. London equals 1, if the couple lives in Greater London, and 0 otherwise. Your estimates are the following. So we can see here we've got some coefficients for our variables. We can see that we've got a constant of 0.877. We can see that there is a negative relationship between net current income and the ratio of food expenditure. We can see that the number of kids increases the ratio of food expenditure, which is completely fine because kids eat fucking everything, don't they? And living in London slightly increases the ratio that you're spending. Okay. On the basis of the above estimates, establish if food is a necessity or a luxury. Now, there is a formal definition of this. Okay. Generally, necessities have, I believe, it may be price elasticity of demand. Yeah. But there's a definition where either price elasticity of demand or income elasticity of demand is between 0 and 1, and that's the definition of necessity. But I'm going to go on a more intuitive thing. So if we look at the coefficient of income, we can see that essentially if the coefficient of income increases, no, not the coefficient of income, if the net current income of an individual increases, then the ratio of food expenditure that the ratio of their food expenditure judged in reference to the rest of their income is going to decrease. So essentially they're going to spend a smaller percentage of their income on food if they have a higher income. This sort of makes sense. If you get more money, you don't necessarily spend more on food in a proportionate way. So for example, if I was to get a pay raise today, I wouldn't instantly start buying more on my weekly shop because it would make sense to me. I'm good with what I eat currently. Okay. We also see that, for example, if the ratio of food expenditure to income were to increase, net current income would decrease necessarily, in the inverse sort of sense. Yeah. So if we basically say that, yeah, we can see that the ratio of food expenditure to income decreases as income increases, which is the quality of a necessity. So we can sort of just go about that. Now there is another way of looking at it. Give me one moment. All right. You guys can see here that we've got the income elasticities here. So a normal good is a necessity, generally, if it is between 0 and 1. Then that's generally what we say. So if the income elasticity is between 0 and 1, then we generally say that it's going to be a necessity. Now we can generally see here that as, let's say, one increase happens, like an increase in, yeah, so we've got a logarithm here as well, and the ratio. So it's going to be a percentage increase. An increase in 1% of the ratio of food expenditure will have a negative effect. So it'll be definitely between, because you can see our coefficient is definitely in that range. If that makes sense. Anyway, yeah. So let's establish the statistical significance of the coefficient of London. Now, to establish statistical significance, we're going to use a t-test. Hopefully you guys know how to do a t-test by this point. I set my null hypothesis as basically the coefficient for London equals 0, and my alternative as it's not equaling 0. If you guys know how to do a t-test, I shouldn't have to take you through this. You're minusing the actual coefficient by your null estimate of the coefficient over the standard error, which is given here. This gives you 2.16 as your t-statistic, which proves that it is basically a statistically significant result valid to the 95% confidence level. Anything above 99% confidence level would be too high. So 95% confidence level is a good thing to cite here. Also, listing the t-statistic for the 95% confidence level at 1.96, and given that 2.16 is larger than that, therefore it works. You want to explain that as well, just to make sure you get enough detail. Okay, further, compute the income elasticity for a hypothetical couple living outside London, with mean log income and no children. Now, how do we calculate that income elasticity? Well, let's have a look at this up. Income elasticity formula. Okay, looking at most online things, we can see quite a clear relationship. The income elasticity of demand is the change in the quantity demanded over the change in the income, and the percentage change, remember. Okay, so let's go back. First of all, let's look at our regression here. You can see that I've listed out the regression. We've got WFOY equals 0.877 minus 0.155 NCY, and then the rest of the coefficients, essentially. Now, these people have no kids, okay? So we're basically going to fill in 0 for kids 2, 0 for kids 3, and because they're living outside London, we're filling in 0 for London as well. So we're really only considering the constant and their income is the main thing, okay? So what we get here, after putting in the mean value of the income, okay, we get the change, essentially, in the ratio of food expenditure to income, which we judge to be 0.183685. Okay. All right, great. So now that we've got that, we generally... Oh, hold on. Yeah. So what we do then is that we also need... So that is... Yeah. Yeah, so we see that the ratio of food expenditure to income. So that's what we're consuming. So that's the percentage change in what we're consuming. So we're essentially saying that given the change in income, we're essentially going to consume 18% more is what's going to happen. Now we want to think about, okay, how much did the income change? Well, we can see here our coefficient for income is 0.155. So that's essentially, the coefficient is telling us how much has income changed, and it's changed by about 15.5% for every 1 unit change, really. So we also have 15.55%. You can also see the formula here. If I go back to the, where is it? There it is. You can see the formula in week 6, lesson 1. I'm using just this formula here. And because actually we've already got a log and a ratio situation, we don't need to translate it too much. So we're good in this form. So what we're essentially going to do, quite simply, is we're going to do 0.813685 over the change in income, which is going to be 0.155. This is around 1.187, although hold on, let me make sure that is completely correct. I want it to be as accurate as possible. Then we're dividing by 0.155. 0.185 is more realistic. Hold on, I need to adjust my estimates. 3685. So then we need to update our values here. 50645 16129, which we can round to 1.185 essentially. So that's our income elasticity of demand that we've got. Okay. The last one's pretty easy. It has been suggested that a share of budget spent on food is a good indicator of household living standard. Households spending a lower share of their budget on food are regarded to be better off. If a number of young children, kids too, in a household were to increase by 1, how much would the logarithm of net income need to rise to preserve the household's living standard? Now, what we actually have to do here is we essentially have to trade off between two things. So if we increase the number of kids by 1 unit, we're going to see that the coefficient dictates that the WFOY is going to increase by 0.026, essentially, in percentage terms. So that's what we sort of get. So we need to counteract that, okay? Now, in order to counteract that, we need to find a way to basically reduce it back to our original. And the only way we can really do that is through the income. Because income is a negative relationship as opposed to a positive one, it's the only thing we can really use to turn it back. So we need to think about, what value of income can I put in here such that this value is essentially going to be minus 0.026. Okay, so minus 0.55 times something equals minus 0.026, essentially. As you can sort of see here, you can just represent it as that sort of, if you look at my notes, you can represent it as just an algebraic form of minus 0.026 is equal to minus 0.115 times x, where x is our percentage increase in the income. And we get about 16.7 or 16.8%. So we'd see that income would need to rise by 16.8% in order to counterbalance this change, essentially. Okay, cool. I think that's all. This one wasn't too bad, I don't think. It's not too challenging, but hopefully it should be fine. I think the main thing is it's a bit confusing in places, especially with the question 2. I think a lot of people will feel that's a bit tricky, but I think it's all right. overall, for me at least. Okay, I think that's all for today. Hopefully you guys are having a nice... I think this is going up on Thursday. Hope you guys have a nice Thursday. I don't know if I would, but let's hope, I guess. Yeah, hopefully everything goes well. And yeah, I'll see you guys later. Always the weirdest outros. Okay, bye.